Hello students, this is Subramania RM, Assistant Professor, Department of Civil Engineering, VCT, Puttur, Mangalore. So in my previous session, I had discussed about numericals with respect to losses of prestress. So today in this session, I am going to continue the discussion with respect to numericals on losses of prestress. So first let us consider a question which was appeared in one of the semester examination. So the question is, in a post tension beam of length 12 meter, a cable is laid symmetrically with its central 6-meter length horizontal and two straight end portions sloping up to an angle with horizontal whose tangent is equal to 0.075. The cable is tensioned by jacking at one end and is anchored at the remote end of the beam. At the jacking end, the measured stress is 1040 Newton per millimeter square. The Obel coefficient K may be assumed as 0.004 per meter. Calculate the stress in the cable at remote end and the 2 points where the alignment of cable changes. Assume coefficient of friction between cable and duct as 0.4. Then what is the percentage loss of prestress between the jacking end and anchored end? So here in the question it is given that a post tensioned beam and length of a beam is 12 meter. So in this beam a cable profile is provided in such a way that the cable is having horizontal profile for a length of 6 meter at its central span, and the cable is having two straight end portion sloping at an angle of 0.075 radian. So for this case we need to calculate what is the percentage of loss of prestress between jacking end and the anchored end. So let us consider a beam. So this is a beam of span 12 meter. So as per the question, it is telling that the beam is having a cable profile with horizontal profile for a length of 6 meter at its central span. So from here to here it is 6 meter, it is horizontal, and on either ends for a length of 3 meter, the cable is having sharp slope. Here it is having a slope at an angle of 0.075 with respect to horizontal plane. Similarly on this side also for the remaining 3 meter the cable is having sharp slope and the angle with respect to horizontal is 0.075 radian, and we need to calculate what is the percentage of loss of prestress due to friction. So in the question it is given that the cable is being pulled from one end. So let us consider the cable is pulled from this end. The cable is being pulled from end A and end D is anchored. So is telling us to calculate what will be the initial stress or what will be the initial force at B, at C and at D. So we know the relation stress is equal to force by area. So using this relation we can calculate stress at B, C, D, as well as we can also calculate force, that is pre-stressing force at B, C, D. Now what are the data given? It is given that theta 1. So this is theta 1. So they have given that the angle of this slope from B to A is 0.075. So this is 0.075, then this is opposite angle, this will be 0.075 radian. Similarly this side 0.075, so this will be 0.075. Let us consider this as theta 1 at A and at B. So with respect to horizontal, the angle between B to C is 0. So theta 2 is equal to 0. Similarly, the angle at C with respect to horizontal between C to B, it is 0. Therefore, theta 3 is 0. And theta 4, that is the angle between D to C, it is 0.75 radian. So theta 2 and theta 3 is equal to 0. Theta 1 and theta 4 is equal to 0.075 radian. So here, when the cable is pulled from this end, when the cable is pulled from A, where there will be loss of prestress due to friction. So here we can get the friction loss at B and at C. So the maximum loss will occur at B and at C because here the alignment of cable is changed at B and C. The alignment of cable is being changed. Hence, at these 2 points we can get maximum loss in the prestress. Now, firstly, let us consider the portion A to B. So the cable has been pulled at A. Then what will be the force, effective force, pre-stressing force that will be available at B? So what will be the loss of pre-stress between A to B? So first let us consider the portion AB. So loss of pre-stress in the portion AB. So we know formula to calculate the loss due to friction. So loss at the portion AB due to friction, F naught into mu theta plus Kx. So F naught A is nothing but it is the initial pre-stress available at A. F naught A is the initial pre-stress available at A. So the loss in the portion AB is equal to 1040, that is given in the question. 1040 is the initial pre-stress applied at one end, that is at end A. 1040 into mu is given 0.4 theta. So angle between A to B is theta 1 and theta 2. So theta 2 is 0 and theta 1 is 0.075. Therefore, theta 1 plus theta 2 is equal to 0.075. So theta is equal to 0.075 plus K is 0.004 per meter. It is given in the question, and X is equal to L. Because the cable has been pulled from one end, therefore X is equal to L. So the length of cable from A to B is 3 meter. Therefore, loss of prestress between A to B or in the portion A to B is equal to 43.68 Newton per mm square. So here the initial stress was 1040 Newton per mm square, and by this stress, by reaching the point B by this time, by traveling a distance of 3 meter, there is a loss of 43.68 Newton per mm square. Then what is the initial stress available at B? So therefore, pre-stress at B, let us call it as FSI at B. Initial pre-stress at B is equal to pre-stress at A minus losses of pre-stress in the portion AB. So pre-stress, initial pre-stress at A was 1040 and loss between A to B we have calculated, that is 43.68. Then what will be the effective initial pre-stress at B? So that will be 1040 minus 43.68. Therefore, the initial pre-stress at B will be 996.32 Newton per mm square. And now coming to the next portion, B to C. So in the portion B to C, what will be the loss of pre-stress? I know that at B, the available pre-stress is 996.32 Newton per mm square. So what will happen for this pre-stress by the time it reaches C? What will be the loss between B to C? Let us consider that condition. Loss of prestress in the portion BC. So in this portion, so here, what is the angle between B to C with respect to horizontal? It is 0. That is theta 2 is equal to 0. Similarly, at C, what is the angle between B to C with respect to horizontal? It is 0. Therefore, theta 2 is equal to 0 and theta 3 is equal to 0. Therefore, theta 2 plus theta 3 is equal to 0. So theta 2 plus theta 3 is equal to 0. Therefore, theta is equal to 0. And the formula for friction is same. So loss of prestress in the portion BC is equal to FSIB. So FSIB means it is the initial prestress which is available at the joint B. So FSIB into M mu theta plus Kx. So mu theta is 0 because theta is 0. Therefore, this term vanishes. Therefore, FSI initial prestress available at B is 996.32 into K is given 0.004 per meter into 6. So 6 is the length of this span between B to C. So here X is equal to L because the cable is pulled from only one end. Therefore, X is equal to 6. This length from here to here it is 6. Therefore, loss occurring between B to C, the loss between this point and this point is equal to 23.9 Newton per mm square. Therefore, prestress at C is equal to FSI at C. That is what is the initial prestress available at C. FSI at C is equal to 996.32. So this was the initial prestress available at P. So by reaching C, what will be the loss? It is 23.9. So after deducting this loss, what will be the initial prestress available at C? That will be 972.4 Newton per mm square. So this is the initial stress available at C. And now at C, the stress is 972.4 at this point. At this point C, the initial pre-stress is 975.4 Newton per mm square. Then by the time this stress reaches the next point D, what will be the stresses at D? So what will be the loss that will occur between the point C and D? Between the point C and D, what will be the loss? So loss of pre-stress in the portion CD. So in the portion CD, the angle at C with respect to horizontal is 0 and the angle with respect to horizontal at D is, that is theta 4, which is equal to 0.075. Therefore, theta is equal to theta C plus theta D. So theta C is 0 plus 0.075, that is theta T. Therefore, theta is equal to 0.075 radian and x is equal to 3 meter. So x is equal to L. So L is equal to 3 meter. From C to B, the span is 3. So x is equal to 3. Therefore, loss due to friction FSI at C. So FSI at C means we are calculating the loss of friction between C to D, and we know the initial pre-stress at C, and the initial pre-stress at C is 972.4 Newton per mm square. So the formula is FSI at C into mu theta plus K into X. So this is the value which we have got in previous step. Mu is given in the question. So theta is 0.075. K is given in the question. And X is 3 meter. Therefore, loss due to friction is equal to 40.84 Newton per mm square. So the loss of pre-stress between C to D is equal to 40.84 Newton per mm square. Then what is the pre-stress available at D? Therefore, pre-stress at D is equal to FSID, that is initial pre-stress at D is equal to 972.4 minus loss. So this is the stress available at C. So initial stress available at C minus loss between C to D, that is 40.84. Therefore, initial pre-stress at D after the losses is equal to 931.56 Newton per mm square. Therefore, percentage loss of pre-stress in the cable is equal to 1040. 1040 is the initial pre-stress minus 931.56. So 931.56 is the initial stress which is available at the other end. So there is a loss of 40 plus 23.9 plus 43.68. So that is the total loss between A to D. So for 1040 minus 931.56 by initial pre-stress 1040 into 100. So percentage of loss of pre-stress is equal to 10.42%. So the loss of pre-stress is within allowable limit, hence the member can be used satisfactorily. Now let us consider one more example. So the question is, a pre-stressed concrete beam 150 by 300 mm is pre-stressed by 10 wires of 8 mm dia with an initial stress of 1200 Newton per mm square, with their centered at 80 mm from soffit. Find the maximum stress in the concrete immediately after transfer, allowing only for elastic shortening. Then, due to creep and shrinkage, and there is a relaxation of steel of 4%. Estimate the final percentage of loss of pre-stress. The total shrinkage stress is equal to 3 into 10 to the power of minus 4. Ultimate creep strain is equal to 4 into 10 to the power of minus 6 per unit stress. EC, that is Young's modulus of concrete, is equal to 35 kilonewton per mm square, and ES, Young's modulus of steel, is equal to 210 kilonewton per mm square. So here the question is given that we need to calculate the losses that is induced in a cable. So here it is a pre-stressed concrete beam of size 150 by 300 mm, and it is pre-stressed with 10 wires and diameter of each wire is 8 mm. So this wires is subjected for initial stress of 1200 Newton per mm square. So here he has asked us to calculate all the losses with respect to the pre-stress, but one thing what he has specified is he has specified to calculate the maximum stresses in the concrete immediately after transfer, allowing only for elastic shortening. That means first we should calculate what will be the maximum stresses in the cable after allowing for elastic shortening. So we know the formulas to calculate the different losses, and we also know that what are all the data required to substitute in the formula. So first let us calculate the total area of the cables. So total area of tension steel. So there are 10 wires and diameter of each wire is 8 mm. So 10 into area of each wire, which gives us 502.65 mm square, and it is given that initial pre-stress FSI is equal to 1200 Newton per mm square. Therefore, initial pre-stressing force is equal to, that is F naught is equal to stress into area. So initial stress is given 1200, area is 502.67. Therefore, initial pre-stressing force that is applied to the cable is equal to 6.03 into 10 to the power of 5 Newton. And in the question he has given that the cables are having an CG with respect to the soffit. So he has mentioned that the centroid at 80 mm from the soffit. That means the cables are placed at a distance of 80 mm from the soffit. From the soffit means from the bottom. Therefore, the depth of a beam is 300 mm. It is a rectangular beam. Therefore, the centroidal axis of a beam will be d by 2. That is y1 is equal to y2 is equal to 150 mm. And what will be the eccentricity of a cable? So d2 is 150 mm and the cables are laying at an distance of 80 mm from the soffit. Therefore, the remaining length or the eccentricity of the cable with respect to centroidal axis will be 150 minus 80, that is 70 mm. So 70 mm is the eccentricity of the cable. So cross section of a beam A 150 into 300 4.5 into 10 to the power of 4 mm square. This is the cross section of a beam, cross section area of a beam. So modular ratio. Modular ratio is defined as the ratio of Young's modulus of steel to ratio of Young's modulus of concrete. So Young's modulus of steel is given and Young's modulus of concrete is given. So the modular ratio will be 6. Since the cable is having concentric eccentricity, that is the cable is straight in nature, therefore stresses induced in the concrete Fc is equal to F naught by A plus F naught by I into E square. So F naught is initial pre-stressing force, A is the cross-section area of the beam, I is moment of inertia, E is eccentricity. So we know what is F naught. So F naught we have calculated here. F naught is equal to 6.03 into 10 to the power 5 Newton. Area we have calculated 300 into 150. I is moment of inertia, so it is rectangular section. I is equal to BD cube by 12. B is 150 and D is 300. So 150 into 300 cube by 12. That gives 3.375 into 10 to the power 8 mm to the power 4. And eccentricity is 70 mm. So 70 mm it is minus 70 mm because the cable is below the centroidal axis and it is minus 70 mm. So substitute the values in this formula. That gives us Fc is equal to 6.03 into 10 to the power 5 divided by 4.5 into 10 to the power 4 plus 6.03 into 10 to the power 5 into minus 70 square divided by I. I is 3.375 into 10 to the power of 8 mm to the power 4. Therefore, compressive stresses is equal to 22.15 Newton per mm square. So this is the compressive stresses induced in the concrete with respect to the CG of a cable. Now, he has asked us to calculate what will be the maximum stress in the member immediate after elastic shortening loss. So what will be the maximum stress in the cable after elastic shortening loss? So first let us calculate what is loss due to elastic shortening. So loss of pre-stress due to elastic shortening of concrete is equal to M into Fc. So MFC because it is a pre-tensioned cable. Suppose if it was a post-tension cable, then it will be half into MFC or it will be 0. So M into Fc, M is modular ratio we have calculated in the first step, that is 6, and Fc we have calculated in previous step 22.15. So 6 into 22.15 which gives 132.9 Newton per mm square. Therefore, maximum stress in the concrete immediately after transfer allowing only elastic shortening of concrete is equal to FSI, initial pre-stress. So initial pre-stress in the concrete is 1200, it is given, minus loss due to elastic shortening, that is 132.9 Newton per mm square. Therefore, the maximum stresses in the member after allowing for elastic shortening will be 1067.1 Newton per mm square. So this will be the stress in the member after loss due to elastic shortening. And now he has also asked us to calculate the loss due to creep of concrete, shrinkage of concrete, as well as relaxation of steel. Now, in the second case, let us take up loss due to creep of concrete. So we know the formula for creep of concrete is equal to delta C by delta C into ES. So here, please make a note. Ultimate creep strain is given. Creep coefficient is not given. So when ultimate creep strain is given, the formula to loss due to creep of concrete is equal to delta C into ES, where delta C is equal to C into FC, and C is nothing but it is the ultimate creep strain. So ultimate creep strain is given in the question. It is 4 into 10 to the power of minus 6, and FC is the compressive stresses in the concrete with respect to CG of the steel. Therefore, delta C is equal to 8.86 into 10 to the power of minus 5. So substituting this value in this formula, therefore loss due to creep of concrete is equal to 8.86 into 10 to the power of minus 5 into 2.1 into 10 to the power of 5. So 2.1 into 10 to the power 5 is Young's modulus of steel, which is given in the question. Therefore, loss due to creep of concrete is equal to 18.606 Newton per mm square. In the next step, let us take up loss due to shrinkage of concrete. So loss due to shrinkage of concrete, we have a formula delta S into ES. So delta S is shrinkage coefficient, it is given in the question 3 into 10 to the power of minus 4. ES is Young's modulus of steel 2.1 into 10 to the power of 5 Newton per mm square. Therefore, loss due to shrinkage of concrete is equal to 63.0 Newton per mm square. And the last case is loss due to relaxation of steel. So it is given in the question loss due to relaxation of steel is equal to 4% of initial prestress. So 4% of FSI, 4 by 100 into initial prestress which is applied to the cable is 1200. It is given in the question. Therefore 4 by 100 into 1200, that gives 48 Newton per mm square. Therefore total losses occurring in the cable is equal to 132.9, 18.606 plus 63 plus 48. So total loss is equal to 262.506 Newton per mm square. So here this is the loss due to elastic shortening, loss due to creep of concrete, this is loss due to shrinkage, and this is loss due to relaxation of steel. So summation of all these losses will be the total loss, which is equal to 262.506 Newton per mm square. Therefore percentage loss of pre-stress is equal to total loss by initial pre-stress into 100. Total loss is 262.506, and initial pre-stress which was applied to the cable is 1200 into 100, that is equal to 21.88%. So the percentage of loss of pre-stress is more than 20%. So it is 21.88%, hence the member is not suitable to use in important structure. So this can be used in some secondary structures, or this member can be used in the structure which is of not very important. Now let us move on to the next example. So here the question is, a simply supported beam of span 9 meter is prestressed with a parabolic cable which has a maximum eccentricity of 200 mm at midspan and 35 mm at support. The beam is 250 mm by 500 mm. Area of steel in the cable is 700 mm square. Initial stress is 1000 Newton per mm square. Anchorage slip is equal to 2 mm. Creep coefficient is 1.2. Shrinkage strain is 1.5 into 10 to the power of minus 4. Wobble effect constant is 0.15 per 100 meter. Mu is equal to 0.4. Relaxation of steel is 2%. Modular ratio is 6%. The wires have to be tensioned two at a time from one end to a value of F1 so as to overcome frictional resistance, and then relax to a value of F2 so that immediately after anchorage an initial stress of 1000 Newton per mm square would be obtained at jagged and unjagged end. Hence determine the final design stresses available in the tension steel. Take ES, Young's modulus of steel is equal to 210 GPa. So here in this question, they have not given what is the initial pre-stress applied to the cable. So here what they have given is immediately after friction loss, the stress in the cable at right end as well as at left end will be equal to 1000 Newton per mm square. That is one condition. So here it is given value of F1 so as to overcome the frictional resistance and then relax to a value of F2 so that immediately after anchorage an initial stress of 1000 Newton per mm square could be obtained at jagged and unjagged end. So here he has given two conditions. The first condition is immediately after friction loss, the initial stresses at both the ends, that is F1, should be 1000 Newton per mm square. That is the first condition. So the second condition is the initial stresses in the cable at both the ends immediately after anchorage slippage should be 1000 Newton per mm square. So these are the two conditions is giving. Now let us consider a beam, a rectangular beam of a cross section 250 by 500 mm. So it is given that the beam is having two eccentricities. One is at the support, the cable is having an eccentricity of 35 mm, and at the midspan, the cable is having an eccentricity of 200 mm. So for this, we need to calculate loss due to, first we need to calculate loss due to friction, then loss due to anchorage slip, then we need to calculate loss due to elastic shortening, loss due to creep of concrete, loss due to shrinkage, and loss due to relaxation of steel. So we know the formulas for all the losses. So what are the data required to substitute in the formulas? So we need moment of inertia, we need cross section area of a member or a beam, we need what is the compressive stresses developed in the concrete with respect to CG of a cable. So first let us calculate this data. So firstly, cross section area of the beam A is equal to 250 into 500, 1.25 into 10 to the power of 5 mm square. Area of tension steel. So the total area of tension steel which is subjected for tensile force is given, that is 700 mm square. Therefore initial pre-stressing force is equal to area into initial pre-stress. Therefore 7 into 10 to the power of 5 Newton is the initial pre-stressing force which is applied. So I is moment of inertia, it is BD cube by 12, B is 250, D is 500, therefore 250 into 500 cube by 12 which gives us 2.604 into 9 into 10 to the power of 9 mm to the power 4. And compressive stresses developed in the concrete at level of siege of a cable or a tension steel. Fc is equal to F naught by A plus F naught by I into E square. So here you remember this condition. In previous session we had solved a similar type of problem. So here the cable is a parabolic cable. The parabolic cable, it is having two eccentricities. Here at the midspan the eccentricity is 200 mm. Let us consider it as E1, and at the supports the eccentricity is 35 mm on both the ends, and let us consider the eccentricity at the support as E2. So in previous session we had discussed a problem there. The eccentricity E1 was 250 mm and eccentricity E2 was 0 mm. So here what happens? The stresses in the concrete will be different due to the eccentricity of 200 mm, and the stresses at this portion near the supports will be different due to the eccentricity of 35 mm. So we need to consider the average compressive stresses in the concrete due to both the eccentricities. So first I will calculate the compressive stresses developed in the concrete with respect to 200 mm eccentricity. So I will consider FC1 is equal to F naught by A plus F naught by I into E square. So E square means I am going to consider as E1 square. I am calculating the compressive stresses in the member due to eccentricity of 200 mm. So FC1. So F naught we have calculated, we know what is the area. We have calculated moment of inertia, and eccentricity at the midspan is 200, that is minus 200 because it is below the centroidal axis. So FC1 is equal to 16.35 Newton per mm square. And compressive stresses developed in the concrete due to level of CG of tension steel at the support. So at the support we have different eccentricity 35. So due to this 35 mm eccentricity, compressive stresses will be developed in the member. So what is that stresses? Let us consider it as FC2. So FC2 is equal to F naught by A plus F naught by I into E2 square. E2 square is minus 35 square, that is the eccentricity at the supports. So 7.7 into 10 to the power of 5, that is F naught area F naught, that is moment of this moment of inertia minus 35 square, it is the eccentricity with respect to the supports, and therefore FC2 is equal to 5.93 Newton per mm square. So these are the two stresses developed in the member due to two different eccentricities. Then resultant compressive stresses developed in the concrete at the level of CG of tension steel. So what is the average compressive stress? FC. So FC is equal to FC2 plus 2 by 3 into FC1 minus FC2. So in my previous session, I had explained you how this formula is obtained. So how it is obtained? So if we draw a stress diagram for FC1 and FC2, it will be in the form of a parabolic curve. So by considering a parabolic curve for FC1 and a rectangular portion for FC2, we will get this equation. So average stress FC is equal to 12.88. So here you should remember this equation. So FC is equal to FC2 plus 2 by 3 into FC1 plus FC2. So substitute the values, we will get FC is equal to 12.88. And here rise in cable with respect to support. So rise in cable with respect to support means we need to consider the rise in cable with respect to support, that is at the support the cable is having an eccentricity of 35 mm. Then what is the eccentricity with respect to ends of the cable and this midspan? So if I draw a line like this, I will draw imaginary line like this, then what will be the eccentricity from here to this imaginary line? That is rise of a cable or eccentricity of a cable. So rise of a cable with respect to support R is equal to 200 minus 35. So from here to here it is 200, and from here to here it is 35. 35 means the eccentricity of the supports. So net eccentricity will be equal to 200 minus 35. So theta is equal to slope. So here the cable is being pulled only from one end, therefore theta is equal to slope, and slope is equal to 4r by L, which is equal to 4 into 165 divided by L. So L is span of a beam, it is 9 meter, So in terms of millimeter it is 9000 millimeter. Therefore slope is equal to 0.0733 radian. So theta is equal to 2 into slope. So 2 into slope because the cable is being pulled only from one end. Therefore theta is equal to 0.147 radian. Therefore loss of prestress due to friction is equal to mu theta plus k into x into F1. So here F1 is nothing but FSI, initial prestress. So he has given in the question that after the loss due to friction, the final stress at both the ends of the cable will be 1000 Newton per mm square. Then what should be the initial pre-stress that has to be applied to the cable? So let us take it as F1. So here F1 is nothing but initial pre-stress. So X is equal to L. It is 9 meter. X is equal to L because it is pulled, cable is pulled only from the one end. Therefore loss is equal to 0.4. It is mu given in the question. Theta we have calculated here, plus k is 0.15 per 100 meter. So divided by 100 into 9. So 9 is x. So this you remember here. So the formula is derived in such a way that here the x is in terms of meters. So here no need to convert this into millimeter. So x is equal to 9 meter into F1 or FSI, initial pre-stress. So the initial pre-stress is not given, hence I will keep it as F1 only. Therefore the loss of stress between left end to right end is equal to 0.0723 F1 or 0.723 times of initial pre-stress. So this is the amount of loss. So in the question he has mentioned that the stress at both the ends are same. The stress at right end as well as the stress at left end is same, that is 1000 Newton per mm square. That is, we know that initial pre-stress which is applied at the one end minus friction loss will gives us the stress at the other end. See here, if I am going to apply initial pre-stress at this end or initial pre-stressing force at this end, by the time this force travels to this point, there will be some loss of pre-stress or pre-stressing force due to friction. So the force or stress available at this point will be equal to the stress or force applied at this point minus this friction loss uses the force at this point. So same thing is done here. So initial pre-stress F1 which is applied at the left end minus friction loss. So friction loss is 0.0723 times of initial pre-stress. So after that we will get the final stress is equal to 1000. So it's telling that after deducting the loss due to friction, the final pre-stress that should be available in the cable is 1000. So this should be the final stress available in the cable. Then what should be the initial pre-stress that should be applied at left end? So this is the condition. F1 is equal to F1 into 1 minus 0.0723. Here F1 is taken as a common factor is equal to 1000. So F1 is equal to 1000 by 1 minus 0.0723. Therefore F1 is equal to 1077.93 Newton per mm square. So here if I apply a force or if I apply a stress of 1077 Newton per mm square, then the stress will be equal to 1000 Newton per mm square in the cable after friction loss. So that is the condition given in the question. The condition is the final stress in the cable should be 1000 Newton per mm square after the friction loss. So that we have calculated here. So I should apply a stress, initial pre-stress of 1077.93 Newton per mm square. So in this 1077, 77.93 will be the friction loss, and the final stress available in the cable will be 1000 Newton per mm square. This is the first case. So the second case, what he has told us to calculate is, now you forget about the friction loss. Now coming to the second condition in the question. So in the question he has told that to calculate what should be the initial stress applied to the cable by considering the anchorage slip. So by considering the anchorage slip, the initial pre-stress or initial pre-stress at both the ends should be 1000 Newton per mm square. That means we know the formula to calculate the anchorage slip. So the loss of pre-stress due to anchorage slip is equal to delta A by L into ES. Delta A is given 2 mm, that is slip of anchorage. 9 meter is the length of a beam. In millimeters it is 9000. 2.1 into 10 to the power of 5 Young's modulus of steel. So loss due to anchorage slip is equal to 46.67 Newton per mm square. So by considering this loss, what should be the initial pre-stress that has to be applied to the cable such that after the loss of anchorage slip, the net pre-stress available in the cable will be 1000 Newton per mm square. So that is F2, which is asked in the question. So F2 is equal to initial pre-stress FSI plus loss due to anchorage slippage. So initial pre-stress that has to be in the cable is 1000 Newton per mm square, and anchorage slippage loss is 46.67 Newton per mm square. Therefore, I should apply a stress of 1046.67 Newton per mm square. That means while applying a stress for the cable, I should apply 1046.67 Newton per mm square. In this total stress, there will be a loss of 46.67 due to anchorage slippage. So after that loss, the final stress available in the cable will be 1000 Newton per mm square. So this is the second condition. And now the third condition, what he has asked is to calculate the design stress available in the tension steel. So design stress available in the tension steel means it is the final stress which is available in the steel after deducting all the losses. So already we have calculated loss due to friction and loss due to anchorage slip. Now let us calculate loss due to creep of concrete. So creep of concrete is equal to CCM into FC. So CC is creep coefficient, which is given 1.2, modular ratio 6. FC, it is compressive stresses in the concrete. We have calculated by considering two different eccentricities at midspan and supports. So loss due to creep of concrete is 92.73 Newton per mm square. Loss due to shrinkage of concrete, delta S into ES. Delta S is given 1.5 to 10 to the power of 5, 10 to the power of minus 4. ES is Young's modulus of steel, 2.1 into 10 to the power of 5. Therefore, loss due to shrinkage of concrete is 31.5 Newton per mm square. And loss due to relaxation of steel is 2% of initial pre-stress. That is 2 into 100, and initial pre-stress is 1000. Therefore, 20 Newton per mm square will be the loss due to relaxation of steel. Therefore, the total loss that will occur in the cable is 92.73 plus 31.5 plus 20 plus 46.67 plus 77.93. So the total loss that will occur in the cable is 182.87 Newton per mm square. And what will be the final design stress available in the tension steel. So final design stress or the final stress available in the steel after deducting all the losses will be FSI minus total losses of prestress. So FSI is 1000, initial prestress is 1000 minus 182. 182 is the loss due to different type of losses like shrinkage, relaxation and creep of concrete, etc. It is 182.87. So the design stress available tension steel is 817.124 Newton per mm square. So 817.124 Newton per mm square will be the final stress available in the member, and this stress is responsible to encounter the loads which is coming on the member.